Welcome back. Welcome to the deep dive. I want to start today by asking you a question about how you fundamentally view the world around you.
Oh, this is a fun one.
Right. Because if you really look around, you're probably used to a certain, you know, comforting level of predictability. You expect things to naturally fall into an average.
Yeah, we're hardwired for that.
Exactly.
Yeah.
Think about it. If you walk into a crowded room and meet a completely new group of people, you expect their heights to be somewhere within a very familiar, safe range. You expect the apples you buy at the grocery store to be, roughly the same size as the apples you bought last week.
You're not expecting a 10-foot apple.
No. From the time we are kids, we are deeply trained to expect the world to operate on these average, easily predictable outcomes. But what if I told you that the most important things in life, the massive, life-altering successes, the sudden natural disasters, the events that actually shape the trajectory of our entire world, operate on a completely different set of hidden mathematical rules?
It is a profound shift in perspective, and honestly, once you see it, it genuinely changes everything about how you navigate your decisions.
It really does. On this journey, exploring the deep, often invisible connections between probability, the hidden mathematics governing nature, and how we actually define and achieve success in our own lives.
It connects things that seem completely unrelated. Forest fires, billionaires, casinos.
Totally. And our mission for you today is very simple. We want to shortcut you directly to
Modern
understanding
historians.
these hidden rules. We're going to break down the critical difference between the normal, everyday statistical distributions you were totally used to and something much wilder called power laws.
The Wild West of statistics.
Yeah, exactly. But most importantly, we are going to figure out how you can strategically play the game of life once you know which set of rules is actually running the board. Okay, let's unpack this.
Let's start by grounding ourselves in the world we all intuitively know. The world of the normal distribution.
The famous bell curve.
Right, the bell curve. This world exists entirely because of what we call additive random effects. Think back to that human height example you mentioned earlier. Your specific height is the result of your genetics, plus your childhood nutrition, plus your environment, plus 100 other tiny, independent, random variables.
It's a big math equation of small inputs.
Exactly. When you add all those small random effects together, extremes become virtually impossible. You are never, ever going to walk down the street and meet a human being who is 5 times the average height.
Like a 30-foot tall person.
Right. The biological math just doesn't allow for it because all those tiny additive variables eventually cancel each other out and pull everyone back toward the middle.
So the normal world is safe. It's tightly clustered around the average. But the notes highlight a moment in the late 1800s that completely shattered that bell curve assumption.
Yes, this is where it gets good.
An Italian engineer named Vilfredo Pareto started looking for hidden patterns in human wealth. And he didn't just look at one town. He gathered vast amounts of income tax records from all over Europe: Italy, England, France, Prussia.
A massive data set for the time.
Huge. And everywhere he looked, across all these different cultures and economies, he found the exact same mathematical pattern. And it was absolutely not a normal distribution.
Not even close. Pareto saw that the vast majority of people earned relatively little. Now, that part in itself isn't particularly surprising, but the curve of the data didn't just drop off to zero the way human height does.
It didn't just stop.
No, it trailed out incredibly far, spanning several orders of magnitude. He was finding a small handful of people earning 5 times, 10 times, even 100 times more than the average person.
Which, if human wealth worked like human height,
Finding someone with 100 times the average wealth would be as physically impossible as finding that 30-foot tall person. But in economics, it was happening everywhere.
Pareto used a specific mathematical trick to make sense of this massive spread of wealth. He calculated the logarithms of all these values and plotted them on a log graph.
Yes.
But for everyone listening who might not be a statistician, what does that actually mean? How does that help us understand what he found?
That is a crucial question. Imagine trying to draw a graph where one person has $10 and another person has $1 billion.
You need a piece of paper the size of a building.
You physically couldn't fit it on a piece of paper.
Uh,
Taking the logarithm essentially shrinks that massive, unmanageable scale into something readable. It turns multiplication into simple addition on the graph's axis.
Oh, okay.
And when Pareto plotted his massive, messy curve of European wealth on this special graph, it miraculously transformed into a perfect straight downward sloping line.
Just a straight line out of all that chaos.
Exactly. Specifically, it was a line with a gradient of -1.5.
And what does a -1.5 gradient translate to in plain English?
It means there is a strict, predictable mathematical rule governing the chaos. It means that every single time you double an income bracket, say, looking at people who make $100,000 versus $50,000, the number of people earning that higher amount drops by a perfectly consistent, predictable mathematical factor.
It's locked in.
Locked in. This was the discovery of a power law. It proved that massive extremes weren't just random flukes. They were built into the very fabric of the system.
To really wrap our heads around how drastically reality changes when you step out of our safe, normal world and into the unpredictable world of power laws, an incredible thought experiment.
The casino games.
Yes. I want you to imagine we are walking into a casino and there are 3 different coin toss games we can play.
Let's walk through them step by step because this is where the math gets incredibly revealing. Game 1 is our baseline. You get to toss a standard coin exactly 100 times. Every single time it lands on heads, the dealer hands you exactly $1.
So this is an additive game, just like human height. The probability of flipping heads is exactly 50%.
Right.
50% of 100 tosses is 50. So my expected payout before I even flip the first coin is $50.
Spot on.
If I sit there and play this game thousands of times, the small variations of lucky and unlucky streaks will completely cancel each other out. I will reliably average out to that $50. It's a normal distribution, safe, boring, and predictable.
Exactly. Now we move to game 2. This is where we introduce the concept of multiplication and things start to get weird.
Okay, I'm ready.
In this game, you don't win a flat dollar amount. You start with a single dollar bill. You toss the coin 100 times. If it lands on heads, your total wealth is multiplied by 1.1, meaning you gain 10%.
Okay.
But if it lands on tails, your wealth is multiplied by 0.9, meaning you lose 10%.
Wait, hold on. If I have an equal chance of gaining 10% and losing 10%, doesn't that just leave me exactly where I started?
You would think so. But let's look at the actual math of multiplying those outcomes. Because the returns are multiplying instead of adding, this creates what statisticians call a log normal distribution.
How does that work in practice?
Think about it like this. If you start with $1, flip heads, and gain 10%, you have $1.10.
Right.
But if your next flip is tails, you lose 10% of that $1.10. That drops you down to 99 cents. You flipped one head and one tail, a perfectly even split, but you actually lost money.
That is wild. So most people playing this game are just going to slowly bleed out their cash over 100 tosses.
Precisely. In fact, if you run the simulation, the median payout, which is the amount the average person sitting at the table will actually walk away with, is only 61 cents.
Wow.
You started with $1, and most people leave with less. But here's the catch. Your downside is strictly capped at $0. You can't owe the casino money. However, your upside is mathematically uncapped.
Meaning if I go on a crazy streak.
If you miraculously tossed 100 heads in a row, multiplying by 1.1 every single time, you'd walk away with almost $14,000.
So because there is that tiny microscopic chance of a massive $14,000 win, that rare extreme outlier pulls the overall mathematical average of the entire game up.
Yes.
Even though most people lose, the mathematical expected average payout remains exactly $1.
Which brings us to game 3, famously known in probability theory as the St. Petersburg paradox. This game strips away the normal distribution entirely.
Okay, lay it on me.
In game 3, you start with $1, and the payout simply doubles every single time you toss the coin until you finally hit heads. The moment you hit heads, you take your money, and the game is over.
Okay, let me make sure I had this right. If I flip heads on the very first toss, I win $2.
That's it.
If I flip tails, then heads, it doubles to $4. 2 tails, then a heads, it doubles to $8. It just keeps doubling for as long as I can keep flipping tails.
Yeah.
But since the game stops the second I hit heads, how on earth do I make any real money? What is my expected value here?
Let's break down the expected value tier by tier. The chance of getting heads on your very first toss is 1/2. 1/2 multiplied by a $2 payout equals $1 in expected value.
Okay, makes sense.
What if it takes 2 tosses? The payout doubles to $4, but the probability of flipping tails then heads is 1 in 4. 1/4 of $4 is $1.
Ah.
What if it takes 3 tosses? The payout is $8, but the chance of that specific sequence is 1 in 8. 1/8 of $8 is, again, exactly $1.
I see where this is going. If we calculate the expected value for 10 tosses or 100 tosses or a million tosses, the expected value for every single possible tier of probability is always exactly $1.
Always.
But since there are technically infinite possible combinations of coin tosses before hitting a heads, what does that do to the total?
You just keep adding $1 plus $1 plus $1 forever, meaning the total mathematical expected value of this game is completely infinite.
Infinite.
It has no cap, it spans all orders of magnitude, and if you take all those theoretical payouts and plot them on that log graph we talked about, you get a perfect straight line with a gradient of -1, a flawless power law.
That sounds like a glitch in the matrix. How can an expected value be infinite?
It leads to a truly mind-bending property of power laws that completely breaks our normal intuition. In a normal distribution, like human height, you have a standard deviation, a measurable, predictable width of where the vast majority of results will safely fall.
Right, the fat part of the bell curve.
But in a power law environment like this casino game, the standard deviation is infinite. This means that the more data you collect, the more you measure, the bigger the average actually gets.
So if I try to find the average outcome of a power law, the math just keeps growing. That feels like it shouldn't be possible.
It feels impossible because we don't live our daily lives in a power law.
Even
But it happens because a single, incredibly rare, extreme outlier will completely dominate the entire data set.
Give me an example of that.
Think of it like this. Imagine you are standing in a room with 100 regular middle-class people. You could easily calculate the average wealth of that room. But then the door opens and Bill Gates walks in.
Oh, I see.
Suddenly, the average wealth of that room shoots up to over $1 billion. The average no longer tells you anything useful whatsoever about the typical person in that room because it has been entirely skewed by one singular extreme event. What's fascinating here is how these abstract mathematical power laws actually manifest in the physical, tangible world around us.
Right, by moving from casinos to nature.
Exactly. In nature, a power law almost always occurs when you have two separate exponential functions dancing together in opposition. Take earthquakes as a prime example. The frequency of earthquakes drops off exponentially as they get larger in size.
So big ones are rare.
Right. But simultaneously, the destructive energy released by those earthquakes grows exponentially as the magnitude increases. When you combine those two competing exponential curves, they conspire to create a perfect power law.
I was looking at the notes regarding the physical world, and it brought up this really interesting analogy about taking a simple magnet and heating it up. The notes mentioned heating it to something called a Curie temperature.
Yes, the Curie temperature.
I'm having trouble visualizing how heating a piece of metal connects to the math of earthquakes and billionaires. How does that work?
It's a beautiful visualization of how systems transform. Inside a standard magnet, you have all these billions of tiny atoms acting like little compass needles. At comfortable room temperature, they group together into tidy little domains, all pointing in the exact same direction, which is what creates the magnetic field.
Very orderly.
But as you apply heat to the magnet, you introduce thermal energy. The atoms start vibrating wildly. That neat, orderly alignment starts to completely break down.
If you carefully tune that heat to a very specific exact point, that Curie temperature, the map of those atoms starts doing something bizarre.
Exactly. When you hit that precise temperature, the system reaches what physicists call a critical state. The domains of aligned atoms become incredibly fluid, constantly shifting and changing. But the most crucial part, the signature of this critical state, is that if you zoom in on the magnet, the visual patterns of those atoms look exactly the same.
What do you mean the same?
You see the identical shifting structures whether you are looking at tens of atoms, thousands of atoms, or millions of atoms.
So the system completely loses its sense of physical scale. It becomes what we call scale-free, which means it turns into a fractal.
Precisely. And in physics, whenever you see a system that has lost its intrinsic scale, whenever you observe a fractal pattern, it is a glaring neon sign that you are dealing with a critical state. And critical states, inevitably, always produce power laws. A
Yeah.
brilliant Danish physicist named Per Bak demonstrated this perfectly back in 1987 with an incredibly elegant virtual sandpile experiment.
I really want to paint the picture of this sandpile for everyone listening because it makes the abstract math so concrete. Imagine a totally blank computer grid. The programmers start randomly dropping virtual grains of sand from the sky, one by one, onto the grid.
Just a completely random drop.
Right. At first, it's boring. 1 grain, 2 grains, 3 grains. They just form little harmless piles. But slowly, as more sand drops, those piles get steeper and steeper. Eventually, a pile reaches a critical angle, and a single grain of sand causes it to topple over onto the neighboring squares.
And by simply continuing to drop sand totally randomly, the computer system naturally tunes itself into a critical state. It organizes its own chaos. Once the grid reaches that state, the entire system becomes riddled with what the researchers beautifully termed fingers of instability.
Fingers of instability. That is such a vivid phrase. What does that actually mean for the grains of sand?
It means the entire board is sitting on a mathematical hair trigger. At that critical point, dropping one single, tiny, seemingly insignificant grain of sand might do absolutely nothing. It might just settle on top.
Oh?
Or it might knock over one neighboring grain, which in turn knocks over 3 more, which knocks over 10, triggering a catastrophic cascading avalanche that sweeps across millions of grains of sand. And when Prubach measured the size and frequency of those avalanches, they mapped onto a perfect power law.
And the true miracle here is something physicists refer to as universality. When a complex system hits that hair trigger critical point, the specific physical details of what the system is actually made of, whether it is grains of sand on a computer screen or vibrating atoms inside a hot magnet, they simply don't matter anymore.
The math takes over.
The math takes over.
Yeah.
They all behave the exact same way. They all universally produce power laws. Here's where it gets really interesting, especially when we look at how we try to manage our own real world. Because nature naturally, inevitably tunes itself to these critical states all the time. Let's talk about forest fires.
This is a perfect real-world application.
In June of 1988, a single ordinary lightning strike started a fire in Yellowstone National Park. Now, that is totally normal. Thousands of lightning strikes happen every single year in forests, and usually they burn a few acres of brush and just naturally fizzle out. But this specific fire was a monster.
Over the course of a couple of months, that single fire merged with other small fires and exploded into an uncontrollable megafire. It burned 1.4 million acres.
Which is insane.
To put that in perspective, that is roughly the size of the entire state of Delaware. It was an astonishing 70 times bigger than any fire ever recorded in that park's history. But here's the crucial takeaway for everyone listening. There was nothing physically special about that specific lightning strike. The spark was perfectly average.
So if the spark was average, why did it burn down the size of Delaware? It's because the forest itself had naturally grown into a state of self-organized criticality, just like the sandpile.
Exactly like the sandpile.
Over the years, the trees, the dead wood, and the dense underbrush had naturally formed those exact same fingers of instability. The entire forest was sitting on a hair trigger, perfectly ripe for a massive avalanche of fire. Which brings us to a massively flawed, though well-intentioned, human intervention. I was reading the notes on the U.S. Forest Service's old 10 a.m. policy.
Yes, back in the 1930s, the U.S. Forest Service implemented a strict rule that every single reported forest fire must be completely suppressed and put out by 10 a.m. the following day.
Which sounds great on paper.
Naively, from a normal distribution mindset, this makes total sense. If you diligently put out all the small fires, you will never have to face a big one, right?
But if we apply what we just learned about the sandpile to a real forest, if you artificially put out all the small natural fires, aren't you just preventing the harmless little avalanches? You are essentially letting the sand pile higher and higher. By suppressing the small fires, the forest never gets to naturally burn off its dense patches. You aren't preventing a fire. You are artificially forcing the forest to build up those fingers of instability. You are literally guaranteeing that when a fire inevitably escapes your control, it will be a world-ending megafire.
Precisely. You are building a bomb. And we see the exact same critical state mechanism operating deep in the Earth's crust with earthquakes. The massive tectonic plates beneath our feet are constantly slipping and grinding in tiny microscopic ways. Most of the time, it is totally harmless.
But the tension builds.
But the Earth's crust naturally organizes itself into a critical state. In 1995, a massive earthquake struck Kobe, Japan. The ground physically shifted by up to 2 meters, and tragically, over 6,000 people lost their lives.
And the truly terrifying part, based on the math, is that the physical geological process that caused the massive devastation in Kobe is the exact same physical process that causes a microscopic tremor that you can't even feel while sitting in your living room.
There is no difference in the spark.
A small slip just happened to trigger a cascade along a fault line that was already primed in a critical state.
Which brings us to a profound real-world consequence for all of us. It means that extreme events in a power law system are fundamentally mathematically unpredictable. You cannot look at the average history of a system to safely predict its future.
I imagine the insurance industry had a really hard time with that concept.
They absolutely do. The entire concept of insurance is built on the comforting math of normal distributions, predicting average risks and average payouts over a long period of time.
Because they think they are playing game one from the casino.
Right. But in 2018, a horrific megafire essentially destroyed the entire town of Paradise, California. The local insurance company covering that area, Merced Property and Casualty, had relied on historical averages to build their financial reserves.
And what happened?
They thought they were playing game one. But when the power law event happened, when the massive infinite standard deviation outlier struck, they were completely wiped out. They went entirely bankrupt. You simply cannot use normal bell curve thinking when you are living in a power law world.
So what does this all mean? How do you, listening to this deep dive right now on your commute or at your desk, actually use this dense mathematical information? It all comes down to taking a hard look at your life and identifying which game you're actually playing.
That's the key.
You need to ask yourself, in my career, in my business, in my creative hobbies, am I operating in a normal distribution environment or a power law environment?
Let's break down the difference practically. If you are managing a local restaurant or running a commercial airline, you are playing a normal game. These businesses have strict physical caps. An airline only has a fixed number of seats on the plane. You physically cannot fit 1 million passengers onto one flight on a Friday to make up for a really slow Tuesday.
It's the exact same constraint with a restaurant. You have a fire code. You can only flip a physical table so many times in one night. So success in a normal game demands consistency. You have to show up and deliver average, reliable, solid, daily performance day in and day out.
But many of the most impactful wealth-generating industries in the modern world are actually power law games. Venture capital, book publishing, tech startups, content creation on the internet. These fields are completely uncapped and are entirely dominated by extreme outliers.
The statistics on these industries are mind-blowing. Y Combinator, which is one of the most famous and successful startup accelerators in the world, once calculated their returns. Out of 280 startups they funded, a massive 75% of their total financial returns came from just 2 single companies.
Just 2.
Bloomsbury Publishing grew into a massive global empire, essentially because of one wild, unpredictable outlier. They took a chance on a book about a wizard named Harry Potter. On YouTube, less than 4% of all uploaded videos ever reach 10,000 views, but that tiny, microscopic fraction of content accounts for over 93% of all views on the entire platform.
And that is because the internet itself is fundamentally structured on a power law. In the early 2000s, a brilliant researcher named Albert Laszlo Barabasi actually proved this by running a simulation. He wanted to know why a few websites had millions of links pointing to them, while most had almost none. He realized the internet grows through a simple snowball effect.
The preferential attachment.
Yes.
Basically, when a person creates a new web page, they naturally want to link to pages that are already famous and popular, like Google or Wikipedia. It is a mathematical rich-get-richer dynamic. His simulation showed that this simple human behavior naturally produces a perfect power law with a gradient of -2, which perfectly matched the actual real-world structure of the internet.
So, if you analyze your life and realize that your career path or your specific creative pursuit or your new business venture is actually a power law game, your entire strategy has to radically change. Your goal is no longer to safely avoid risk or to grind out a consistent average daily return.
Your ultimate goal becomes persistence over consistency. You have to make repeated, intelligent, small bets. You have to willingly roll the dice again and again and again, fully knowing and accepting that the vast majority of your attempts will completely fail or do absolutely nothing.
I mean, it's dropping sand.
Exactly. You keep dropping those grains of sand because you know the math. You only need one massive runaway outlier to pay for everything else.
If we connect this to the bigger picture, Human beings are not magically exempt from the physical and mathematical laws of the universe. We often arrogantly think our intelligence allows us to bypass these rules, but we are deeply embedded in the exact same mathematical reality as the earthquakes and the sand piles.
We are part of the system.
Recognizing whether the specific challenge currently sitting in front of you requires additive randomness, where you should absolutely be steady, safe, and consistent, or multiplicative randomness, where you must be bravely, relentlessly, and almost stubbornly persistent. That is the ultimate key to actually navigating the modern world successfully.
It honestly changes how you view everything you do. And I want to leave you with a final thought today that builds on everything we've just discussed. What if our own internal personal growth, our own deep creative breakthroughs, actually operate on a power law?
That's an interesting angle.
In school, we are heavily trained to expect linear additive progress. You study for an hour, you get exactly an hour's worth of smarter. It's a bell curve. But what if mastering a truly difficult, complex skill, or finding your actual life's passion, doesn't work like that at all? What if it requires long, highly frustrating periods of small failures and false starts?
Like dropping grains of sand that do nothing.
Exactly. What if every time you try and fail, you aren't actually failing, but you're just dropping single invisible grains of sand, slowly building up your own internal fingers of instability? Until one day, one tiny, seemingly insignificant new piece of information triggers a massive, critical state avalanche of insight that completely redefines who you are and what you are capable of.
That is a truly beautiful and empowering way to look at human potential. Sometimes the breakthrough you are waiting for isn't a steady, predictable climb up a ladder. It's a sudden, mathematically inevitable cascade.
So figure out exactly which game you are playing today. Keep dropping your grains of sand and never stop questioning the hidden rules of your world. Thanks for joining us on this deep dive. We'll catch you next time.